So after taking so many pictures of Comet 3A Atlas, and after seeing the Comet 3A Atlas several times, here is what we know now.
Independent astronomer Ray spent 5 hours photographing 3I Atlas. He started at 1 in the morning and kept shooting until clouds rolled in around 4:30, and he saw something he wasn't expecting. When he reduced the exposure to see the core clearly, he noticed structures, not random jets, not chaotic gas, structures that look like blades, 2 or 3 of them, spinning. Ray has been photographing this comet for weeks. He's watched it tumble. He's tracked the jets. But these images are different. The blades have definition. They have shape. They're organized. So what are they? What Ray saw. Most people who photograph comets use long exposures. You want to capture as much light as possible. You want the tail to show up bright and clear. That's how you normally do it. Ray tried something different this time. He shortened the exposure, way down. He didn't want the bright center to blow out into a white blob. He wanted to actually see the core, the thing itself, not just the glow around it. Here's why that matters. When you take a long exposure of something bright, the center gets overexposed. It turns into a bright spot. All the detail is gone. You get a beautiful tail. You get a nice, fuzzy glow. But the actual object in the middle? Just a blob of light. Short exposures fix that problem. You lose some of the faint stuff around the edges, but you gain detail where it counts, right in the middle. And with 3I Atlas getting closer to Earth right now, that detail matters. We have a short window to study this thing before it's gone forever. Ray also used something called comet alignment. This is a stacking trick that makes the comet sharp. Normal astrophotography stacks images to reduce noise. You take 100 pictures. You line them up based on the stars. Then you combine them. The stars stay sharp. Random noise gets averaged out. Everything looks cleaner. But comets move. If you align on the stars, the comet blurs. It becomes a streak across your image. The stars are sharp. The comet is mush. Comet alignment flips that. You line up all your frames on the comet instead. Now the comet stays in one spot. The stars streak. But who cares about the stars? The comet is what we're here to see. And now it's crystal clear. So Ray had hours of data. Short exposures, comet aligned. Clean images of the core without overexposure. He combined multiple frames to reduce noise. He applied sharpening filters carefully to bring out detail without creating artifacts. And when he zoomed in, he saw something weird. The object isn't round, it's elongated. Potato-shaped is how Ray describes it, and it's tumbling end over end. You can see the rotation if you watch the time-lapse. One end, then the side, then the other end, then back again. That part isn't unusual. We already knew 3I Atlas was rotating. Previous observations showed a rotation period of about 16 hours. An oblong object tumbling through space is totally normal for a comet. Most comet nuclei are irregular shapes. They're not perfect spheres. They're chunks of rock and ice held together by their own weak gravity. But that's not what got Ray's attention. It's the blades. Think about what a normal comet looks like up close. We have images from spacecraft missions. Rosetta visited Comet 67P. Deep Impact smashed into Comet Tempel 1. Stardust flew by Comet Wild 2. In all those images, you see irregular rocky surfaces. You see jets of gas and dust coming from specific spots. But the jets themselves are fuzzy. They're plumes, they're clouds. They don't have hard edges. What Ray is seeing looks different. The structures have definition. They're not just glowing gas. They look like physical objects, like fins or wings or blades attached to the nucleus. And as the object rotates, these structures rotate with it. Ray sees what look like 2 or 3 blade-like structures. They're rotating with the object. They have edges. They have shape. They're not just gas spraying randomly in all directions. They look organized, structured, deliberate. He describes them as looking like a spinning wheel. Imagine one of those old-fashioned windmills, the central hub in the middle, then blades extending out from it. Except this windmill is tumbling through space at tens of thousands of miles per hour, and it's billions of years old. The blades aren't solid objects. They're made of gas and dust. But they're organized gas and dust. Like there's something creating them, something making them take that shape, instead of just puffing out in random directions, and the jets themselves aren't behaving like normal comet jets. Normal comet jets are messy. Gas escapes from cracks in the surface. The direction changes as the comet spins. The intensity goes up and down as different parts heat up and cool down. You get bursts. You get puffs. You get irregular plumes going every which way. These jets look different. Ray describes them as having a flapping motion, like they're moving in wind. They're turbulent, but they're also maintaining their shape, like there's something physical causing them, not just random gas escaping from surface cracks. Here's another weird thing. The jets seem to be coming from specific locations on the nucleus, and those locations stay consistent as the object rotates. With a normal comet, you'd expect the brightest jets to be on the side facing the sun. That's where it's hottest. That's where ice sublimates fastest. But with 3I Atlas, the jet pattern doesn't match that simple model. The brightest emissions aren't always on the sunward side. They're coming from specific features on the surface. And those features are aligned with the blade structures Ray is seeing. When Ray sharpened the images even more, the structure became clearer. The blades are there, the organization is there, and once you see it, you can't unsee it. And that's when Ray hit a problem. The bias problem. Ray stopped himself. He realized he was starting to see everything through a filter. Here's what he means. When you think you're looking at a comet, your brain interprets everything as comet behavior. Random jets must be outgassing. Irregular brightness, sublimating ice. Tumbling motion, uneven shape. Every observation fits the comet framework because that's what you expect to see. Same thing happens if you start thinking it's a spacecraft. Structured jets, propulsion system, organized features, engineering, rotation, controlled spin. Everything confirms what you already believe. This is confirmation bias. It's a real problem in science. Once you commit to an explanation, your brain filters data to support that explanation. You notice things that fit your theory. You ignore things that don't. Ray caught himself doing this. He was looking at the blades and thinking, these look like spacecraft components. Propulsion blades, rotating structures, engineered parts. But he knows that's dangerous, because human brains are really good at seeing patterns, sometimes too good. We see faces in clouds, we see shapes in random noise, we see structure where there isn't any. So Ray made a choice. He's not going to think of it as a comet. He's not going to think of it as a spacecraft. He's going to look at the data without assuming either one. And that opened up a third option. What if it's neither? Comets are dirty snowballs, ice and rock loosely held together. They sublimate when they get hot. They fall apart easily. They're fragile. Spacecraft are built objects, metal and composites, designed for specific jobs. They don't sublimate. They don't shed material randomly. 3I Atlas doesn't quite fit either description. It's shedding gas. That's comet-like. But it's been doing this for billions of years. It's been traveling through interstellar space, getting bombarded by cosmic rays, exposed to hard radiation. If it were just a ball of ice, it should have evaporated long ago. We should be seeing a small dead rock, not an active object shooting out jets. It has structure. That's unusual for a comet, but it's rotating chaotically. That's unusual for a spacecraft. So what else could explain it? Ray's hypothesis is a planet fragment, not a whole planet, not even a moon, a chunk of a planet, maybe from a collision billions of years ago, maybe ejected when the planet was destroyed or torn apart by gravity. Here's why that idea is interesting. Planets aren't uniform balls of rock. They have layers, like an onion or a hard-boiled egg. The outer layer is the crust. Solid rock, relatively cold. This is what we walk on. Below that is the mantle, hot rock that flows slowly over millions of years. This is what drives volcanoes and plate tectonics on Earth. At the center is the core, heavy metals like iron and nickel, still hot from when the planet formed. Radioactive elements decay and generate more heat. Now imagine a giant planet somewhere in the galaxy, billions of years ago. Something catastrophic happens. Maybe it gets too close to another planet and tidal forces rip it apart. Maybe it collides with something huge. Maybe its star goes supernova and blasts the planet to pieces. Whatever happened, chunks of that planet get ejected, scattered into interstellar space. Most of the pieces are just crust and mantle, cold rock. But some pieces might include fragments of the core. And here's the key part. The core material stays hot. Radioactive decay keeps generating heat. Not enough heat to melt the whole fragment, but enough to drive activity. Enough to melt ice that's mixed in with the rock. Enough to create volcanic vents. Enough to release gas. A fragment like that could stay active for billions of years, long after any ice on the surface should have evaporated away. Long after it should have become a dead rock drifting through space. This would explain why 3I Atlas is still shooting out gas. It's not just solar heating making surface ice sublimate. It has a furnace inside, a chunk of planetary core keeping it warm from within. And it would explain the organized jets. If there are volcanic vents connected to the internal heat source, they'd be in specific locations, fixed to the object. As it rotates, you'd see jets coming from the same spots over and over, not random puffs from all over the surface. The blade appearance could be material being channeled through these vents. Imagine a geyser on Earth. The water shoots up in a specific direction because it's being forced through a crack or pipe. Now imagine that happening in space with almost no gravity. The material would stream out farther, it would maintain its shape longer. And if the object is rotating, that stream would trace out a curved pattern, maybe even a blade-like pattern. It's speculative. Ray knows that. But it fits the observations better than the standard comet model. And it's testable. And here's the thing, it's testable. If this is a planet fragment with an active interior, it should have specific characteristics we can measure. The gas emissions should include volcanic gases, not just water and carbon dioxide. Things like sulfur dioxide, nitrogen compounds, gases you'd expect from volcanic activity. The heat signature should show hotspots that don't correlate with sunlight. If it's just a comet, the warmest parts should be the side facing the sun. If it has an internal heat source, you might see warm spots elsewhere. The jets should line up with surface features, not just with where the sun is shining. Cracks, vents, specific locations on the surface. Those are all things telescopes can measure. If we look. What happens next? Ray is making his data public. He's not hiding it. He's saying, here's what I captured. Look at it yourself. Tell me what you see. That's how this should work. One person seeing something unusual isn't proof of anything. It's a data point. It becomes meaningful when other observers see the same thing, when multiple independent observations line up. So what does Ray's data actually show? The time-lapse shows clear rotation. The object is tumbling. It's elongated and it's spinning end over end. That's confirmed. The sharpened images show structure in the jets. Not just a fuzzy glow. There are edges. There are boundaries. There are features that show up in multiple frames. That's real. The blade-like appearance? That's where interpretation starts. Ray sees blades. You might see something else. Ridges, wings, lobes, asymmetric jets. The data shows structure. What that structure represents is still up for debate. But here's what we know for sure. 3I Atlas has been weird for months. The anti-tail pointing toward the sun, the persistent activity, the structured emissions, and now these blade-like features in close-up images with the core properly exposed. Is it a planet fragment? Maybe. That would explain some things. But it raises other questions. Where did it come from? If it's a planet fragment, which planet? From which star system? How did it get ejected? What destroyed the planet? We don't know. We can make guesses, but we don't have enough data to trace it back to one specific system. How big is the core? If there's an active planetary core inside, how much of it survived? Is it a tiny chunk? Or is the whole thing basically core material? We don't know. Hubble estimated the overall size at somewhere between 300 meters and 5 kilometers across, but we can't see inside. We can only guess based on the activity we're seeing. What's it made of? Rock, metal, ice? All three? We have spectroscopy data from Webb and other telescopes. We know it's releasing carbon dioxide, water vapor, carbon monoxide. Those are normal comet gases. But are they sublimating from sunlight, or being released by internal heat? That distinction matters. How long will it stay active? If it has an internal heat source, does it eventually run out, or does it just keep going? We don't know. This is the only interstellar object we've seen that's this active, and it's different from the other two we've found. Oumuamua was the first interstellar object we discovered. It passed through in 2017. It was small, maybe 100 meters long, cigar-shaped or maybe pancake-shaped, depending on who you ask, and it showed absolutely no activity, no coma, no tail, no gas, just a tumbling chunk of rock that flew through the solar system and left. But Oumuamua did something weird. It accelerated slightly as it left. Not much, just a tiny push that couldn't be explained by gravity alone. Some scientists think it was outgassing we couldn't see. Others proposed more exotic explanations. We never got a good answer because it left too fast. Borisov was the second interstellar object. It showed up in 2019, and it looked exactly like a normal comet. It had a bright coma. It had a tail. Spectroscopy showed water vapor, carbon monoxide, cyanide. All the usual comet chemicals in normal proportions. It was just a comet that happened to come from another star system. Nothing particularly mysterious about it. 3I Atlas is different from both. It's active like Borisov, but it's not acting like a normal comet. The chemistry is unusual. The anti-tail pointing toward the sun is unusual. The organized jet structure is unusual. And now these blade features are unusual. It's not inert like Oumuamua, but it's not normal like Borisov either. It's somewhere in between. Or maybe it's something entirely different that we haven't seen before. The observations continue. Ray is still imaging it. Other amateur astronomers are tracking it. Professional telescopes have it scheduled around December 19th when it reaches closest approach to Earth. That's when we get the best data, highest resolution, best signal to noise, detailed spectroscopy of the jets, thermal imaging to look for hotspots. Here's what astronomers will be looking for: spectroscopy of the jets. Not just what chemicals are present, but where they're coming from. If there are volcanic gases mixed with normal comet volatiles, that would support the planet fragment idea. Thermal imaging. Infrared telescopes can see heat. If this is a normal comet, the warmest spots should be where the sun is shining. If there are warm spots elsewhere, that suggests internal heat. High-resolution imaging of the nucleus. What's the exact shape? Are there craters, ridges, vents? The more detail we see, the better we understand what we're looking at. Precise rotation measurements. Is it spinning uniformly, or is the rotation changing? Jets create torque. By measuring spin changes, we can figure out how much force the jets produce. All of this needs to happen now. After December 19th, it gets farther away. Images get fuzzier. Signals get weaker. By mid-2026, it'll be too faint to see. Then it's gone. Back into interstellar space forever. This is our only shot. And then maybe we'll know more. Or maybe we'll just have better questions. December 19th is 5 days away. The clock is ticking. This thing is passing through once and then it's gone forever. If we're going to figure out what it is, we need to do it now. Ray captured something unusual. Blade-like structures rotating with 3-eye atlas. Jets that have organization and shape. He's not claiming to know what they are. He's showing the data and asking you to look. So what do you see? Comet outgassing? Structured emissions from a planet fragment? Something else entirely? Let me know in the comments. And subscribe, because Ray and other observers are still tracking this thing. December 19th is coming fast, and we'll know a lot more after that closest approach.